Beth Rose and Grant, doing my last final video. I'm going to start with the physical object in a typical classroom. I'm going to talk about dilation. Dilation is the same object, different sizes. So I have a nesting doll I want to show you a quick video of. See how this black nesting doll, you're going to open it up and there's another one inside and another one inside. What you'll notice is that they are exactly the same object, just different sizes. Next one is tessellation. Tessellation is when objects are fit together, and the first thing I thought of was a checkerboard. We have checkerboards in our class, and see how they all are together. Also, another example is chess. Chess is also one of these, and I want to show you another one. Giraffe spots. Look how they all fit together beautifully. That's a tessellation. Also a honeycomb, a honeybee's honeycomb. Look at that, tessellation. See how they all go together? The next one is a rhombus that is not a square. And I immediately thought of a diamond. A diamond is not a square, but it does have 4 sides that are the same. It is also, I thought of a baseball diamond. When you play baseball, I know some of you guys do play baseball, but I don't know if you've ever looked up or if you had the opportunity to even see this. A baseball diamond here, if you look at it, it's in the shape of a diamond. The green part is the baseball, is the diamond. And then we have cards, the diamond on a face of a card. Diamond playing card. There you have a diamond. 4 sides, same, but they're not a square. And that's the only ones I thought of. How about parallel lines? Parallel lines, something in our classroom. I couldn't think of anything in our classroom that's parallel lines, but I could think of a road, like when you're with your mom in a car and you look at this is a good picture of a road. Here is the top or where the grass line is, and where the next road is, that's parallel, like a car. I guess you could think about our that's what I thought of, our salt and pepper lines that we use when we walk down the hall. There is a silver line on each side of our feet. Remember, that's parallel lines. We also have concentric circles, and I thought of a pirate steering wheel, a pirate ship steering wheel, because concentric circles are a set of circles that have the same center but different radii. So you think of this, a pirate ship's steering wheel. See how that's one big circle and then another little circle in between. So they're the same side. They have the same radii, or same center, but different radii. Next one is angles of a triangle. If an angle of a triangle is obtuse, can another be obtuse? Why or why not? And no, it can't be. By definition, an obtuse triangle has only one obtuse angle and 2 acute angles, because the sum of all angles in a triangle must be 180 degrees. If you have 2 obtuse angles, the sum exceeds 180 degrees, which is impossible with a triangle. So you can see if I got 2 of these, that's not going to turn into a triangle. Can you have one angle of a triangle be acute and the other 2 angles be acute? Yes, you can, because all 3 angles are less than 90 degrees. Acutes are less than 90 degrees, and their sum is always 180. So yes, the remaining 2 angles can also be acute and add up to 180 without exceeding it. What did I just read? Oh, 3. If a triangle has 1 acute angle, it's necessarily an acute triangle. No, because a triangle with 1 right angle and 2 acute is a right triangle. No, because with acute, all angles equal 180. It can also be an obtuse angle or obtuse. It can be obtuse and have 2. It can have an obtuse triangle having 1 obtuse and 2 acute. Last one, can 2 angles of a triangle be supplementary? No, because a triangle cannot have supplementary angles. Supplementary angles are two angles that add up to 180 degrees. And that's only two angles. We need three to make a triangle, so that won't work. I'm now going to explain to you the surface area of an irregular flat object. I used a leaf like a holly leaf because it is the Christmas season. So we have to decide what the surface area of this holly leaf is. The first step that we're going to take, I can show you what I did, is I took and I marked every single square that was whole. So you can see the X's are the full. So I had 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I had 15 holes. And then I did different slashes for each one. So then I had 6 that were more than half, like more than half full, 8 that were less than half. And then I did the equation, 15 full, so that's times 1, and then there were, oh, it erased, dang it, 0 that were more than, or that were half, because there wasn't any that were quite half, 6 that were more than half, and 8 that were less than half. So then we add those together. 15 times 1 is 5, 15 times 1 is 15, 0 times 1/2 is still 0, 6 times 1, and you got 21 square inches. I did the same thing here with this heart. I looked at the heart, did the same thing. I tracked and I looked. And so which ones were all full? So you can see with the big X's, there were a lot that were full. Then I did a dot for ones that were just half full. Just half full. One that were more half, or a single, like looked like a 1 or a slash. For more than half, I did a line. So you can see the same thing I did here. I found 35 full, put that in the equation. 4 halves, that's the dots, 1, 2, 3, 4 was down here. And then this forwards, or the one for more than half. And then some that were less than half, I did these straight lines, so you can see them here. This is how we figure out how to find out the square units of objects that are not regular. These are irregular. So we did the equation again, 35 times 1 plus 4 halves plus 9 ones, and 6 were less than half. So it's 35 plus 2 plus 9, 37 plus 9 equals 46 square units. You are using it with a geoboard. The squares represent how much. So you could have done, I think I saw one example, you could have just taken this line, and kind of indicated it that way, but I just X'd out each different square. I'd like to talk about if you think that constructions with a compass are good for high schoolers. Should it even be taught for high schoolers? And with much thinking, I thought, yeah, because when you get those tools out, it helps open your students' mind. It gives them a different view of math, and it provides, provides hands-on opportunities to make connections and to have like an abstract reasoning or learning. There isn't that much of hands-on in math. It's not like art class or gym class or, but you do have these tools, then blocks, abacus, but I think it is still good to do that in high school. In grade school, it's a little different because they're not even that big into geometry. So I'm thinking of, it helps you to visually see things. I think that's what the spatial reasoning, visually seeing them. It helps with, I think, building, helps with their fine motor, learning how to do stuff. They can get the fundamentals of geometry because we all know that when it starts, it's just going to keep going. Can spark a kid's interest because they might be like, that was really cool. And it, like I said before, it's early exposure, critical thinking, even though they don't realize it. And we're going to keep it pretty basic at the grade school level. It still is learning and having fun with learning. So yes, I don't, because I'm not a mathematician or someone who absolutely loves math, that there's not a ton of opportunities to have fun with math. So I thought doing constructions was a little bit of fun. We learned about factorial numbers, or what the factorial, in math, the factorial is represented by what would look like an exclamation point. It's to multiply a given number by every positive integer. So it's used to find how many ways things can be arranged or ordered in a set of numbers. It's an easier way. We see it on a calculator like this exclamation point, and it kind of means like 4 is 4 times 3 times 2 times 1. But when you get into larger numbers, like 1,632, it's going to be repetitive. So we learned about that in class. And when I think I was on Facebook, I found this, upside down, this meme that says, how many strawberries did we squeeze in? 22 plus 1/3 bananas. We used geometry and a mallet. So somebody who reads this would be like, what in the world? But because we learned about the factorial function, we know what that means. So this is how they even find 1.120 million trillion billion, I don't even know what that one is, strawberries. So this, I'm pretty sure they meant like 22 exclamation point, like 22 strawberries did we squeeze in here. But then if you learn geometry, a regular person would think it's 22, but if you know geometry, I guess they're trying to say that there's that many billions of strawberries. I sent you this email and you said that you did find that and you thought it was funny. I think it's funny to see things in the world now that I have had this class. I never would have caught on to that if I hadn't had this class. If I would have just been like swoop, I don't even know what that means, but now I know what that means. I think that was all 5 videos. And I just wanted to do a quick thing here for 1 minute. I just wanted to thank you for being such a great professor. You are really into math, and I am not by nature, and I'm thankful that you had the passion for it so that I could get through this class. And I hope that you have a great holiday and that I did great on these videos.